Part E, let's try and solve this equation here, and we're still looking for all the solutions. Do note that we do not have a trig function isolated here. And again, all the previous examples, we had a trig function equal to a number, and that allowed us to use the unit circle. It allowed us to figure out what angle makes this happen, okay, or what angles make it happen. So we can get this to where it is a trig function equal to a number. In order to get this, we just need to subtract by 2 tangent of x on each side. So if you do 3 tan x minus 2 tangent of x, you will get just a single tangent of x over here, and then we still have the square root of 3 here. So this question really comes down to trying to find all the solutions to just tangent of x is equal to the square root of 3. Let's go find where that happens. Here's our unit circle, and we're really looking for places where y over x is equal to the square root of 3, right? In other words, that's going to happen at places that look like the square root of 3 over 2 divided by 1/2. Okay. That's what we're looking for, where y is the square root of 3 over 2 and x is 1/2. So that will result with tangent being equal to the square root of 3. Okay. So we should have one of these in quadrant 1. Looks like it's right here. And we actually have another one in quadrant 2. And it's not quite the right one there, is it? It would be this one here. Right? If you were to take y equals minus the square root of 3 over 2 and divide that by minus 1/2, you'd actually get the positive square root of 3. Okay, so we have 2 spots here. Let's go ahead and write those down. We had x is equal to pi over 3, and we had x is equal to 4 pi over 3. Now, with sine and cosine, in our previous examples, so what we were doing is we were finding this x value like we did here, but we were adding the period times n to these because we knew every time we did a full rotation, we'd end up with the same x and y values. Okay. Now, tangent's different, right? Its period is just pi. If you just go halfway across the circle, you're going to end up with the same ratio of x and y. Okay. So what that means is instead of adding 2 pi n, we're going to be adding pi n. And something else interesting happens here. Let's go into our calculator, and what we're going to do is we are going to plug both of these little formulas into our calculator and see how their values compare. Okay. We are looking at a TI-84 plus here right now, and in our y equals, we have our 2 formulas that were supposed to give us all the solutions to the equation that we were trying to solve. And there's something kind of interesting about these 2 equations that produce all of our answers. And what we're gonna see here is not the case when we were working with sine and cosine. But let's go into our table here. I'm gonna hit second table. And if you look at the diagonals, you will see all of the same numbers. Okay. So what's going on here is both of these lists contain all of the exact same numbers. So what is the case is we do not need both of these equations. Just one of these will suffice because they're really the same list of numbers. Okay. Now that we're back here in OneNote, what we found is that the list of answers that are generated from this equation and from this equation are the same list. Okay, they're the same list of numbers, so we don't need both of them. So what we're going to do is I'm going to cross this one out just so we don't use it, But I want to point out there was nothing wrong with this. It's just it was redundant. Okay? It was just redundant was all. So this is our answer here. And again, this is where n is an integer. And this is going to happen whenever we're working with tangent and cotangent. But when we're working with sine and cosine, we won't have this issue. And I'll show you kind of real quick here why. When we were working on some earlier examples, we were looking at, say, instead of the pi over 3 over here, let's maybe do the 5 pi over 6 and 7 pi over 6. That was one of our examples. Okay. All right. Now, if we were to go, say, one full revolution from 5 pi over 6, we're going to land always in the same spot. Where essentially, is what I'm saying, is any list of solutions that contains this is not going to contain this solution down here. There's going to be no overlap between those lists. And you can kind of do this as an experiment. If you were to go back up here and say, let's just say the very first example. You could plug this into your calculator, both of these equations, okay, and you'd see that the lists don't share any of the same numbers like we saw with tangent. Okay. And so that's it there for E. Let's go ahead and try D here. So you can see that we actually have a pretty similar equation here because in part E, we wound up just looking at tangent of x is equal to the square root of 3, and now we have tangent of 2x minus pi over 4 is equal to the square root of 3. So the only thing that's really different here is this argument, okay, the thing that's being plugged into tangent. And the idea is we would like what's being plugged into tangent here, or the argument, we would really like it if this were equal to some angle that would make tangent equal to the square root of 3. And we've already done this work up here. That's going to happen at pi over 3 plus pi n. And so all we need to do here is solve for x. Okay. And then we're done. Okay. So we have 2x is equal to, and so I'm going to add pi over 4 to each side. And if we were to do that, we'd have to get a common denominator of 12. And so when we add these together, that should give us 7 pi over 12. And then we still have plus pi n. And we haven't quite finished solving for x here. We still need to divide by 2. And so this gives us x is equal to 7 pi over 24 plus pi n over 2. And again, this is where n is an integer. Next we have cosecant of 6x is equal to negative 2. The first thing that I would note is we do have a trig function equal to minus 2. So that means we could jump to the unit circle right now. However, I honestly prefer to be thinking about sine rather than cosecant. So what I'm going to do here is, instead of looking at cosecant of 6x equals minus 2, I'm going to look at 1 over sine of 6x is equal to negative 2. Okay, and if we were to multiply both sides by sine of 6x, we get 1 equals minus 2 sine of 6x. And if we were to then divide by minus 2, we'd get minus 1/2 is equal to sine of 6x. And so this is going to wind up being the equation that I'm going to use to go look at the unit circle. Again, looking at cosecant would have been fine. This is just a little bit easier for me to think about because now I know I just need to look for x values of -1/2. Those are the angles we want to find. Okay. And remember, we want those angles, or we want what's being plugged into sine here, 6x, we want this to be equal to those things that will make sine equal to -1/2. Let's go to our unit circle. And if y is equal to -1/2, that means we are going to be below the x-axis. Okay. So y equals -1/2 happens here at 7 pi over 6 and also at 11 pi over 6. Let's go ahead and fill that in here. So we have 7 pi over 6, and don't forget your plus 2 pi n, and we also have the 11 pi over 6 plus 2 pi n. And remember, we're just adding the period times n here. So if this were tangent or cotangent, it'd be plus pi n. Okay. Next, we'll just solve each one of these for x. We'll go ahead and we will divide by 6 here. So we're going to get 7 pi over 36. And if you do 2 pi n divided by 3, that's just going to be pi n over 3, because 2 divided by 6 is 1/3. And then over here, we're going to have x is equal to 11 pi over 36 plus pi n over 3. So here's our answers. And before we move on to our next set of examples, I want us to actually think about how do we use these formulas here. Okay, we kind of looked at them on the calculator a minute ago, but exactly how do we use these? Okay, so here's how it works. If you were to plug in any angle described by these equations into this original equation here, it should satisfy it. So in other words, if I were to take, say, cosecant of 6 times, how about 7 pi over 36 plus pi, and then just choose your favorite number for n here. Why not 11? Just choosing a random number here for n. Okay. So if I plug in any integer for n here, it's going to result in a solution to our original equation. And you can test this out. Plug this in your calculator, see that this is true. Okay. And actually, I'll go to my TI-84 right now. What I would like us to do here is actually see how those little formulas that we've come up with work exactly. So the idea is, if we take any numbers that result from those formulas, if we plug them into our equation, it should be a solution. Okay, so if I were to say do cosecant of 6x, or in our case 1 over sine of 6x, okay, would look something like this. But I want us to plug in an x that comes from that formula. And so in OneNote we had written one example of an angle. How about that 7 pi over 36 plus, and then we had pi n over 3. And we chose a specific n. We decided to go with n as being 11. We just chose it at random here. And again, we want to divide this by 3. And this is just coming from our formula. And so what we have here is 1 over sine of 6 times one of those angles, okay, which is really just cosecant of 6x. Okay. And if this really is a solution to that equation, our result should be -2. And it is, so this is good. This formula is giving us solutions. If this didn't work out on your calculator, you may be missing a parenthesis, or maybe your calculator's in degrees. We want to be in radians here.